Okay, so here we have 4.2 logarithmic functions. And so what is this section going to be over, what's going to be about? You have here how, or the definition of a logarithmic function, how a logarithmic function is going to look like. It's going to look like this, basically. Y equals log base b of x. Okay. This is how you read it. Log is the abbreviation for the word logarithmic, or the logarithm. So here they're giving you how you read this, which, this and this is the same thing, instead of the y, f of x. So this function is the logarithmic function with base b. Okay, you can also read this as the logarithm of x with base b. Here it says the logarithmic function. Wait, there's an n here. There should be an n. You can also call this the logarithm. The logarithm. Okay. Now, something that you must know is that an equivalent way, or what's an equivalent? Something that is the same. Another way of rewriting this equation, which is a logarithmic equation, as an exponential equation, it's this one that I circled here in pink. This is an exponential equation. This is called, you already see, a logarithmic equation. You have to know that there will be problems later where you have to rewrite this back and forth from logarithmic equation to exponential equation, or from exponential equation or form back to logarithmic equation or logarithmic form. Okay, so there's two ways of writing an equation, whether it's a logarithmic or an exponential, are interchangeable. Okay, now you need to understand that whatever your y value is in the logarithmic equation, I'm just going to abbreviate: logarithmic equation, exponential equation. Whatever your y is here, that's the y that you see in the other equation, in the exponential. Whatever base b you see on the logarithmic equation, that's the big B that you see here on the exponential equation. Whatever x you see here in the logarithmic equation, that's the same x you see right here, and this should have an equal sign. That's the x that you see here on the exponential equation. So just know that you can go back and forth between these two forms of writing an equation. Okay, logarithmic and exponential. This section is really focusing on logarithmic, but since we learned exponential functions, or about exponential functions in the previous section, it's kind of incorporating that in here. So the first question says, write the following equation in its equivalent exponential form. This is written in logarithmic form, we can see, because it has a log. As soon as you see log, that's the abbreviation for logarithmic. This is a logarithmic equation. They want you to write it in exponential form. The first thing that I would try to do is to find how similar this is to the format of a logarithmic equation, which is this one that I wrote here. It's basically the same, it's just that it's flipped. So let me send the y to the front, just because I know that we are used to seeing the y at the beginning or on the left side of the equal sign. Sometimes seeing it at the end, it confuses us, but it's the same thing. So this, written in logarithmic form, it's written as y equals log base b of 8. So you can already see what y is in my particular, sorry that I put 8 here, it should be an x. Okay. Y, it's a y, that's the same thing, it's a coincidence. B, it's a 2, and x is an 8. Okay. So what we're trying to do is we're trying to rewrite this as an exponential. An exponential equation looks in the following format. If I go back to the previous slide here, b to the y equals x. That's what you're going to copy here. Y should look like an exponent. B to the y equals 2x. So, what's b according to my problem at 2? You can probably write it like this. B is a 2. What's going to be the y? The y is a y. I mean, that's no different. And the x is an 8. So all you're trying to do is find, okay, what's the y, but in my equation, it's a y. Sometimes it's going to be other letters, sometimes it's going to be even a number. Not always has to be, the y has to be the same thing as the same verb. Okay, so all I'm doing is finding the value for y, the value for b, and the value for x, and I'm using them, but in an exponential form. So this would be our answer. This equation right here. Okay. Now we can write an equation that is written in a logarithmic form, in exponential form, or vice versa. Okay. So let's look over here at the next one. Write an equation in its equivalent logarithmic form. Okay, so now this doesn't have an log, a logarithm, so it's not a logarithmic form. Okay. So we have to write it in that form now. This is an exponential form. So first I would try to find how this looks like an exponential. B to the y equals to x. So I'm putting arrows to show you that you already know what b, what y, and what x is. Now you need to rewrite this in logarithmic form. Logarithmic form is y equals log base b of x. So all you need to do is, what's your y? My y here was a 7. What's the base of the logarithm, which is the b? A y. And what's the x? 770. Okay. And that's it. That's what you do. The answers here, when you're writing an equation from logarithmic form to exponential, or backwards from exponential to logarithmic, it's not a number, the answer. It's still an equation, it's an expression. I mean, that's just what it is. All you're doing is rewriting something in a different way. Okay. Next problem. Evaluate the expression without using a calculator. Without using a calculator. So let's learn how to solve a logarithm without the calculator, because the calculator can do this for you, but I'm going to wait to show you how to do it on the calculator, okay? Basically, you have to say the base, this is what you have to think. The base raised to some number has to equal to this number that's right here. Or in other words, what you're doing is you're rewriting this as in exponential form. This right now is written in logarithmic form, log base b of x. Now you don't have the y part, but you can add it here if you want. Okay, so you can say there's a y here. So in exponential form you have b to the y equals to x. Well, if you really look in here and pay close attention, what was your b? The 2. What was the y? A y. What was the x? 1/4. So you can see it two ways. Either change this into exponential form to solve it, or the way of solving a logarithmic form is always going to be take the base, the small number, think this base raised to what number here. So this is the question. What number is going to go here? So that when I do 2 raised to this number, the answer is 1/4. And you may say, how am I going to do this? Because 2 raised to a number to give me a fraction? Well, that's where what I told you in the previous lesson about learning how to deal with negative exponents was going to be very, very helpful. So, if you cannot think right away of, what number would I put here? 2 raised to the negative 2 It's actually 1/4, and you're like, how is that possible? Well, if I go step by step to work this out, remember that I'm supposed to put 2 over 1 to work this by hand. I flip it around. My 2 becomes, the 2 is still a 2, but the exponent changed to a positive, which is what I wanted to be able to do it by hand. And then 2 raised to the second power means 2 times 2, which is 4. So this is how the answer that I'm looking for is what number here. Remember, I put the question mark here. The base raised to some number that equals this answer 1/4. That is equals to this. Well, the number that is going to work, we just found it right here. It's going to be -2. This is what the answer is that you are looking for. Just the -2. So on the computer, probably it's going to say equals and then above. So the answer is just going to be equals -2. Okay, that's what the answer is, -2. So if you were to put this on the calculator, but I'm telling you, I'm going to wait to show you how to do it on the calculator, not yet. That's what the answer would be, just a -2. Whichever number you can use to raise the base to that number to equal this big number that's right here, that's what the answer is that you're looking for. Or basically, you're changing this logarithmic equation into exponential form. Okay, exponential form. That's what you're basically doing. Let's look at the next one. Evaluate the following expression without using a calculator. Let's do the same thing. Let's put a y here. So we say, okay, this is y equals log base b of x. Okay, so y is y. The 2 is going to be the b, and square root of 2 is going to be the x. So, okay, let's rewrite this in exponential form. Exponential form. So that is b to the y equals x. So what's b? Okay, b is a 2. What's y? Just y. What's x? Is square root of 2. So, what's my question now here? What's the number that's going to go in place of the y? 2 raised to some number has to equal to square root of 2. Okay. This is something that you have to start learning and memorizing if it is that you're not aware of it yet. I think at the beginning of the class we went over this, so we're going to retake this. Remember, there was a section about radicals and simplifying radicals and that. Well, remember that we said that you can rewrite, so I'm going to put here, square root of 2 can be rewritten as 2 raised to the 1/2. Where am I getting the 1/2 from? Remember that a square root has a 2 on the outside even though I don't see it. And 2 is raised to the first power here, or you can see as the whole thing is being raised to the first power. All this. Okay. The thing is that you need to understand that this works both ways, from here to here, from here to here. This is just a different way of rewriting a number or an expression using a radical, the root, or using an exponent. The index becomes the denominator of the fraction on the exponent. The exponent inside of this radical, so you may say, what's the exponent? I don't see it. Well, it's a 1. If I don't see it, it's a 1. You can see it inside, 2 raised to the first, or you can see it raised on the outside of the whole root. And that would be your numerator. So due to this fact, how can I make 2 to the y equals to the square root of 2? Well, this y probably has to be 1/2. Because I know that 2 to the 1/2 is the same as the square root of 2. Okay, so this is the same as this. Why? Because you know that we can rewrite this in this form. The 2 would be here, and the 1 could be here on the inside or on the outside, doesn't really matter. So, okay, again, what's the answer? What are you looking for? Whichever number that you can use on the exponent of the base 2 or the number 2 to equal to square root of 2, that's the answer. So the answer again is 1/2. Okay. So it's always the base on the logarithm raised to something has to equal whatever is here in place of x. So this is something that we learned before, but here it is again in case you forgot. Okay, but we went over at the very beginning of the class over different rules for exponents, for radicals, and that's where this is coming from. Okay. Next one, evaluate the following expression without using a calculator. So without using a calculator, we're going to do the same thing. Y equals this. So y equals log base b of x. That's how this is written in logarithmic form. You're going to write it in exponential form. B to the y equals x. I know it doesn't say for you to write it like that, but you see, that's how we've been solving these logarithmic equations without the need of a calculator. So what's b? 81. What's y? Well, just y. What's x? It's a 9. So 81 raised to something has to give me 9. That's a tough one too, because you're going to say, what do I do? The only way that 89 can be equal by raising it to exponent, that can be equal to a smaller number than 81, it's probably going to have to be through using fractions. So what about this? What if I do 81 raised to, because the question is this, raised to the 1/2? And you may be like, again, 1/2, why is that? Because remember that this can be written as the square root of 81 due to what I told you right now. Where is the denominator of the fraction? It's the index of the root. It's a square root. Where is the 1 on the numerator? It's the exponent of the 81. But 81 to the first power, it's 81. So you can see how if you evaluate square root of 81, that's 9, and 9 is equals to 9. Okay. So the number that you need to use as an exponent on the 81, so that 81 raised to that number equals to 9, it's 1/2. So that you can turn it into a root like this. So if you are able to understand the previous problem, then this should make sense to you, like, because it's coming from the same property that I told you here that we learned in the first lesson. Okay. So the answer would be that. So now we're going to learn some properties of common logarithms. Okay. When you have to do the logarithm of base b, the base is going to be, the little b there, it's going to be any number that you want it to be, like whatever number it is in every problem. But when you're doing the logarithm of the number 1, no matter what the little b is, the answer will always be 0. When you have to do the logarithm of a little base and something here that are equal to each other, these two, the little base and the big number that is supposed to be here are the same thing, the answer is 1. When you have to do the logarithm of some base and then whatever is supposed to be here in place of x is raised to an exponent, but then these two are the same again, b and b are the same, but this can be numbers, can be other letters, right? The answer is just the exponent. This is what the answer would be. Here the answer would be 1 in the previous one. And then on 4, it says when you have something raised, I wanted to sneeze, b raised to something, to a logarithm, but when this b is the same as the little b here on the base, the answer is just going to be this x that is right here. Okay. Now, this 1, 2, 3, 4, this first 4, every time it's showing the base as the little b. That little b means that probably that base is going to be different numbers every time except the number 10. Why except the number 10? Because when logarithms have a base of 10, usually that little 10 is not written. Like this one's right here. These logarithms have a base 10. These have bases different than 10. Okay. What's the base? The little b on the logarithms that you see. So here, usually when you have a logarithm on the second listing of the common logarithms, when your base is at 10, usually like technically should be there, like log of 10, but you're not gonna see it written down. So when you have a logarithm base 10 of 1, the answer is always 0. When you have a logarithm base 10 of 10, if these two numbers are the same, the answer is 1. If you have a logarithm of base 10 and then this base and this is the same, the answer is x. You see how these formulas in reality, but this is for when the logarithms have a different base that is not 10, and this is when the bases are going to be 10. So 10 raised to the logarithm of base 10 of x, the answer is going to be x. So this is also like this one. So the same properties hold for logarithms which bases are 10, as well as for logarithms which bases are not 10. Now, can the calculator give you these answers? Probably yes. Okay, but I'm gonna be holding on yet to the use of the calculator. So let's apply. I'm pretty sure the next problems are gonna be applying these properties or common logarithms. Evaluate or simplify the expression without using a calculator. So here we have a logarithm. Apparently I have no base, but I do. Remember that I said when we do not see a base, we assume that the base is a 10. Logarithm base 10 of 10 to the 6th power. Remember what the answer was. When these two numbers are the same, then the answer is just 6. Okay. Now, why is that? If you really want to see an explanation, like you can try to memorize this so that you can do it faster. But if you want to know why, it's because, remember, how would you solve this? We usually say, how to solve the logarithm expression. We would say the base raised to something has to equal what I have on the x part. Because what number is going to have to be here if I want this side to equal this side? Well, it has to be the same number as this one, no? That's the reason that the answer is 6. Okay, so it's kind of simple, but at the same time, if you try to memorize these general properties or these common logarithms when the base is 10, the answer comes out even faster. Instead of you thinking, how do I solve this and how do I do it? Just learn the properties and the common logarithms. Okay. Here we have a base, okay? Log, I know it looks like if it was 7 raised to the 7, but this little 7, it's the base of the logarithm. So remember, when this number and this number are the same, the answer is 1. How could that be? Explanation of, or how to solve it, just like I did right now. Explanation for this. The base, this little number, raised to something has to equal what I have on the x part. Well, what's the exponent that I can see on this 7? What's the exponent that I have even though I cannot see it? Well, it's a 1. So what exponent should I put here? 1. That's why the answer is that. Okay. See, I'm telling you, these ones are very, very simple. but you just need to know and understand the rule and understand basically how to evaluate a logarithm so that the rule can make sense to you. This one, you have a logarithm base 8 of 1. So remember, if I go back to the logarithms, when my base is something that is not 10, I'm talking about some of these first 4 general properties. When there is a 1, like number 1 here, there is a 1, I'm talking about this one, the answer should be 0, no matter what the base is. So here, the answer is 0. Now, why is that? Explanation again. You are supposed to take the base, raise it to some number so that this can be equal to the x part, to 1. This is a definition that by now you should try to remember. 8 raised to what number is going to give you 1? To 0. The only number that, when it's an exponent, and you raise anything to that number, it equals to 1 is 0. Okay, that's something that we have talked already about before. Now, we're going to enter into something that is called LOG. It's logarithms. Natural logarithms is a way of, it's another kind of logarithms, okay? But they're called natural because they're written in a little different way. And natural logarithms don't have bases. You see how logarithms have base 10, base 8, base 2. Well, these ones don't have a base. I mean, not that you can see it. They do have a base, that is the base e. The logarithmic function with base e, it's called the natural logarithm function. But you're never going to see the base e actually shown in the natural logarithms. The way to write a natural logarithm, it's this way. LN. LN stands for natural logarithm. Okay. So the function, the logarithmic function with base e, is usually expressed in this form. So when the base here is an e, that's when we're going to be talking about natural logarithms. But usually, I mean, we're never going to see the logarithms written with the base e in this form. Usually natural logarithms are just written in this form that I put in the box. So that's all you need to know. What's a natural logarithm function looking like? Ln of something, in this case of x. What's the Ln abbreviation for? For natural logarithm. Okay. LOG is just logarithm, regular. And those you do see the basis. Now here we have properties of natural logarithms. Okay. So we already saw all these properties right now in this slide over here. Here. You see how they were common logarithms when the base is 10 for these regular logarithms? Well, now we have some rules for natural logarithms, where apparently I don't have a base, but the base is e, right? So it's helpful if you kind of memorize this one. Natural logarithm of 1 will always be 0. Natural logarithm of e will always be 1. Natural logarithm of e to the x will always be x, the answer, this exponent right here. E raised to the natural log of something, the answer will be that something, that x right here. Okay. So let's see how we apply this natural logarithms properties. Evaluate this. Okay. So in the previous lesson we learned, and I'm gonna rewrite this, that when you have a fraction, if you flip around this fraction, so instead of you having 1 over e to the 9th, let's write e to the 9 over 1. When you flip around a fraction, the exponent changes to the opposite sign. So now what's e to the negative 9 over 1? Well, in reality, I do not even need to write the 1 on the denominator, because anything divided by 1, the answer would be the same thing. So all I did is flipped around, do the reciprocal of the fraction. Because of that, you need to change the sign on the exponent to the opposite. And now I'm going to apply one of the properties that we saw right now. When you have ln of e raised to something, so let's look at number 3 right here. E raised to something in a natural log, the answer is the exponent. So here, the answer is just going to be this number right here. Okay. Now, how could that be? Remember that supposedly the base is an e here, it's just you're really not going to see it. So when these two bases are the same, it's like this one, like number 3 over here. When these two bases are the same, the answer is just the x, the exponent. Okay. So that's what the answer would be. Next slide. So that was just an application of one of the properties. I should probably show you by this point that you can use the calculator, right, for the logarithms. Where do you find the regular logarithms? Here, log. Let me go back to a previous slide before I do this one. Like for example, this one. Now, the thing with these calculators, these old version calculators, is I do not think that you have the ability to, let me just double check, to enter a logarithm, no, with a different base than 10. So for example, if you were trying to enter log base 8 of 1, the calculator is not going to do the right thing if you just put log of 1. Here it's telling you the answer is 0, because these calculators, at least mine, this old version, only do logarithms in base 10. The calculator assumes that you're saying that the base is 10, when in reality in this problem that we are seeing on the screen, the base is 8. So there's something that is going to come later that is called the change of base formula. But for you to get, and still it gave me an answer of 0, but I mean that's not really the right thing. Change of base is entering log base of 1 divided by log base of 8, and it gives me that answer. So it's a coincidence that I put log base of 1 and it gave me a 0, okay? But in reality that would be wrong, because the base in the calculator, when I enter the first the first log, it's assuming that the base is 10. Change of base formula is entering the second way, when you have bases that are not 10. Log of 1 over log of 8. Okay, and that would give you 0. For example, for this one, log of 7, the big 7 first, divided by log of the base. It's always the big number and then over the base. And see, it gives me 1. Okay. I don't know if probably I put log of 7 only, it's going to give me a different answer. See, that's wrong. That's not the answer 1 that should be. Because the calculator is thinking that the base is 10, when it's really not. The base is 7. So you need to let the calculator know that the base is not 10 by writing it in this form. Log of the big number divided by log of the small number. That is called the change of base formula. I think it's coming later, and I probably got ahead of myself already. But I wanted to show you where the logs are, at least. Now for the ln, where is the ln? Ln is right here. Ln of 1 divided by e to the 9th power. Close the parentheses at the end for the first parenthesis you opened. I'm sorry, that was my dog barking like crazy. He got scared. Yeah, so what I was saying is that the ln, where do you find it? Right here, under log, under the log. And you enter it just the way that you saw me enter it. 1 divided by e to the 9th, and you see how the answer was still the same thing as I got without the calculator. Okay. So, moving on to something else. Characteristics of logarithmic functions of the form, and you can see here the form of the function, or how a function of a logarithmic function should be written. And so several characteristics that we need to know is what's the domain and what's the range. Domain, it's from 0 to infinity, range is from negative infinity to positive infinity, and we don't see the graph here, but I can probably do the graph here for you. Log of x doesn't really show us a good picture, but this is how the logarithm, the basic or the parent function of the logarithmic functions are supposed to look like this one. I know you don't see it, but it looks like a curve right here, if it was something like this. And in reality, I mean, I'm telling you, it's impossible to graph it in a way that it doesn't look like it's touching the x-axis, but in reality, this graph now has a vertical asymptote right here, overlapping the y-axis. There is a vertical asymptote at x equals 0. You can see why the domain is from 0 to infinity, why the range is from negative infinity to positive infinity. This arrow, it's supposed to keep going lower. Okay, this right here. It's gonna continue going this way. So that's the domain and the range. All logarithmic graphs that are like the basic pass through the point 1, 0. These ones do have an x-intercept of 1. So supposedly here this one passes through 1. There is no y-intercept. Why not? Because now we have a barrier here or an invisible wall at the vertical asymptote of x equals 0. So it's never going to touch or cross the y-axis in reality because of that vertical asymptote. On 3, if b is greater than 1, we have a graph that goes up to the right and is an increasing function. And if it is between 0 and 1, the b, then it's going to be a graph that goes down to the right and is a decreasing function. Okay. And then the same thing on 5, it's about the vertical asymptote at x equals 0. Okay. So the y-axis turns into a vertical asymptote. So the graph approaches but never touches the y-axis. Okay. So let's see how it goes doing this graph. So graph 5 to the x and the logarithmic, the log of x with base 5 in the same rectangular coordinate system. So graph them in the same rectangular coordinate system. Okay. So you already know how to graph an exponential by hand. So to do faster this, I'm gonna get the points from the table. So let's choose a couple of them. Let's say -1, 0.2, 0.1, and 1.5. Okay. And then over here for this one, if we understand, or I should say with this problem, you're gonna realize of something. But let me graph this one. How would you put this equation in the calculator? So I'm gonna make here to type in the calculator. This is how you're gonna put it. You're gonna put log of x divided by log of 5. This is how you're gonna put it on the calculator. This is called change of base formula. And why do you need to do this? Because I already explained to you right now that the calculator does not recognize any logarithms with different bases other than 10. So you need to let the calculator know that the base is 5, and this is your way of letting the calculator know. So log of x divided by log of 5. Okay, so we see the graph. Let's look at the table. Okay. Let me do something really quick. Okay. Yeah, so I was telling you how to enter it, right? And I was going to show you something else. Sorry. So log of x divided by log of 5, just the way that you see me entering it on the calculator, you're going to put it also. You graph it. What I did right now is, if I go to my table, I changed it to, for me to be able to enter numbers on the x and for the calculator to give me the answer. Where do I go? I've been telling you several times, but second window, I went to the independent variable and I set it to be asked. I enter on it. So when you go to the table, now you can type numbers. So I type 0.2. So if you see, what I'm going to do is I'm going to choose the y values that I have here. I'm going to choose them to be my x's now on purpose. 0.2, the answer is -1. If I put a 1, the answer is 0. If I put 5, the answer is 1. How could it be that the numbers are switched, are flipped, if this is an exponential function and this is a logarithmic function? Well, exponential and logarithmic functions are inverse functions of each other. That's a concept that you must know, and you need to memorize it, since right here for later uses. Exponential and logarithmic functions are inverse functions of each other. That's the reason that, if you remember the sections about inverse functions, we said the domain of the original becomes the range of the inverse, as well as the range of the original becomes the domain in the inverse. They're switched. Your x and y values are switched, basically, in inverse functions. So we're going to put here f of x and g of x are inverse functions due to exponential and inverse functions being due to exponential, not inverse, and logarithmic functions. Functions being inverse of each other by definition. That's something that you must memorize. This is something important. And because of that is the reason that the x's and the y's are flipped. So how do I know that these are inverses of each other? Look, if I change this exponential function to logarithmic, I'm going to get exactly the function that you see here, as well as if I change the logarithmic into exponential, I'm going to get exactly the function that you see here. We already know how to switch an equation from exponential to logarithmic and from logarithmic to exponential. Okay, so we graph the original, 5 to the x, or the first equation, not the original, but the first one, -1.2, 0, 1, 1, 5, 1, 2, 3, 4, 5. This one, remember that it has a horizontal asymptote. right here at y equals 0, right? Then we plot the points for the other graph. 0.2, -1. So 0.2 and -1 is going to be somewhere here. 1, 0 here. And 5, 1, 2, 3, 4, 5, 5, 1. Sorry, not 5, 0. 5, 1. So this one is going to look like something like this. Remember that we said that this kind of functions have not a horizontal but a vertical asymptote at the y-axis. So vertical asymptote, and I'm just gonna put asymptote at x equals 0. Okay. So remember when we talked about inverse functions of each other, the x's and the y's are switched. Also, if you put that special line that goes in the middle of these two, the y equals x, if you remember that line, these two graphs should look like a mirror image across those two, across this line. I know I'm not a perfect, and my picture is not perfect, but more or less you can see how they're inverses of each other. So that's what you needed to learn with this problem, that exponential equations are inverses of logarithmic equations. Okay. So, next one. It says begin by graphing log of x with base 5. This one. Oops, I wanted another color. That's the original. Then use transformations of this graph to graph the given function. What is the vertical asymptote? Use the graph to determine the function's domain and range of this one. Graph the function this, graph the asymptote of g of x as a dashed line. You don't really need to graph both. I mean, I was graphing both in the previous section, the original and the transformation. Here it doesn't say. I really do not know if on the online homework they're going to ask you to graph both or just one. It looks like just the transformation. But still we need to go through, if they want us to do the transformations by hand or they want us to learn how to do the transformations by hand, then this is what you want to do. I mean, you're really going to go step by step. So at first I'm going to graph this on the calculator, the original. So log of x divided by log of 5. Remember, it's always log of whatever is here in place of the x, and then the log of the base goes on the denominator of the fraction. And I don't know why I put a parenthesis here. Okay, there. So you graph it. Let's get some points. Oh, in my table. Let me fix it. Auto. So don't start with 0 error because that's what's going to be. So start with 1 0. You can use 5 1. If I can avoid the decimals, I know that I've been using them and it's fine. But I just said, what if there is really numbers that have no decimals? That would be simpler. I don't think the rest are just going to be decimals. So let's choose a third point. After that one, we can choose 9 1.4. Why up to 9? Just because. I don't know. So I'm not gonna graph that one. I'm gonna start doing the transformations according to how they're supposed to be. I only see one transformation here, as a matter of fact, the plus 8, and I did a mistake here because I forgot the equal sign. Okay, so what's that plus 8 going to do? The same thing as you know that adding or subtracting a number through the inside of a parenthesis does. It's gonna shift horizontally your graph 8 units to the left. That means you're gonna subtract 8 to every x coordinate or x value from the previous table. 1 minus 8 is negative 7, 5 minus 8 is negative 3, 9 minus 8 is negative 1. The y's stay the same. And that's the only transformation you need to do. So let's graph only the transformated version because it doesn't say for me to use to do the other graph. So let's just save time. 1, 2, 3, 5, 6, 7, negative 7, 0, 1, 2, 3, negative 3, 1, and negative 1 with 1.4. So if we really want to know how this graph is going to look here, I can already foresee how it's going to look. But if you go here, that was the original graph, log of x plus 8, all that goes to the top of the fraction divided by log of the base. Now your x is like becomes all this thing here. So okay, see how I'm putting it? So I graph. Okay. And you can see how I know that it might look like this would be a straight line, but it's not. We need to make it as curvy as possible. So it's something, and I'm telling you, I draw horribly. I'm just not good at this. Yeah, it's increasing slowly. In mine, it looks like it is increasing like a lot. Probably this point I should have put it like a little bit lower, but more or less it looks like this. And it is, as a matter of fact, going to be getting bigger and bigger, like going up here. So this one, okay, you can see more or less that my graph looks like. Remember that logarithmic equations don't have horizontal asymptotes, they have vertical asymptotes. Now where would this one have a vertical asymptote? Well, this point is negative 7, 0. If you see, like the graph, my old version calculator doesn't really show that this line goes down, but it really continues this part of the curve going down to negative infinity. So that means that here at negative 8 there is a vertical asymptote right here that is not letting this graph go to the other side. But technically this should continue be going down. It's just the calculator doesn't do a good job at showing. But your vertical asymptote here is x equals positive 8. So you can already see that, okay, where am I, I'm sorry, not positive 8, negative 8. Where is in the equation that value, or where can you also tell that, not just by the graph or by knowing the definition, but from this plus 8, from this plus 8, that's where this one came from. But it has to be the opposite, because remember, it moves to the left, okay, 8 units, or you subtract 8, that's the reason that it's a negative 8. Instead of just positive 8, the way you see x plus 8, well, it would be with a negative. Just the way we usually think about shifting the graph to the left or to the right with the opposite sign from what we see, well, that's the same thing here for the vertical axis. So I didn't even graph the original. If you really want to see the original, how it would change, you can graph it here if you want, but I'm not gonna waste time in doing the table and graphing it. I mean, we did the table, but I'm not gonna plot the points. So log of x divided by log of 5. Oh my gosh, what did I do? I put everything in the same one. Log of x plus 8 divided by log. Why keeps on putting, oh, because this principle is already divided by log of 5. That is the transformated one, and I didn't click on going below. For the second one, I'm going to put the original log of x divided by log of 5. So that's the transformated version, and over here somewhere it's going to be the original. The second one was the original. Okay. So how you enter this on the calculator? You put log of x plus 8 divided by log of 5. That's how you put it. This one, same thing, doing transformation. So we have h of x is the original. The original, which was this one. And I was already going to do the other. Which, I mean, I know you can do, but if this is asking to do, for you to do the original and use the transformations, let's just learn how to use the transformations. So I graph on my calculator. Let me take away this 2. Log of x divided by log of 3. So it's going to look more or less like that. So I'm going to choose 1, 0, 3, 1, and I'm going to use a decimal. 6 and 1.6. There's only one transformation that I see that happened, and that's the +4. Now, if you want, let's send that number to the end. So you know it's a vertical shifting. So when the graph is shifting vertically, you know that what's changing is the y. So you're going to be adding 4 to every single y. The x's stay the same. So 0 plus 4 is 4, 1 plus 4 is 5, 1.6 plus 4 is going to be 5.6. Okay. So when we plot the points, and probably I can do more space here, this looks horrible. So this was a 6, and this was 5.6. So we plot the points of the transformated graph: 1, 4, 3, 5, 1, 2, 3, 1, 2, 3, 1, 2, 3, one more here, and 6, 5.6, probably there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.6 here. I went too high. 1, 2, 3, 4. 1, 2, 3, yes. 1, 2, 3, 4. Yes. So you want to know how the transformated version should look like? We put, now how are you going to enter this on the calculator? It's very important that on the calculator you're going to put log base 3. The calculator automatically opens a parenthesis for the x, and make sure the +4, you do not put it inside of the parenthesis because it's not what it's meant to be. Nowhere here we see a parenthesis with the plus 4 inside. So make sure that you do not put it inside of the parentheses together with the x. Otherwise, it's going to graph a completely different thing. So first of all, how can we put this in the calculator? You already know. Log of x divided by log of 3 in parentheses and plus the 4 to the side. So log of x divided by log of 3, the plus 4 here. Now, if you want to put like an extra parenthesis here, you can. It doesn't hurt. But still, this would give you the right graph. So you can see how that second graph is where these points are. So my graph is coming from somewhere down here probably, and it's turning and doing this. Yeah, let me see if I can do a better job, but it's just hard to graph this one. See, I always put the last one too high, that I cannot do better than that. So what would be my vertical asymptote here? Let me think about this one. There's something that for some reason I don't like about this one. Let me see. No, it's okay. I was thinking, why is it like this? But all we did is we translated every x, every y 4 units up. Okay. It was a vertical translation or shifting 4 units up. So it makes sense that whatever the asymptote, the vertical asymptote for the original was, which if you see the original, here is your vertical asymptote at the y-axis, the same vertical asymptote for this one, because you're not really moving it to the side. You just moved up 4 units. So vertical asymptote is still x equals 0. Okay. So this parenthesis that I put here at the end is optional. If you put it or you don't put it, it's still gonna be fine. Okay. These points don't look anymore the way they used to. So 3, 5. There. Okay, now we have to do the transformation of ln of x. So the original and then we'll say what happens when you have a negative in front of the x. But I think we talked already about this. So the original, go here ln, put an x, you graph it. Let's look at the table and let's copy some points. See, it's a logarithmic function, it's the same thing, but instead of using log, you use ln. That's the only difference. So 1, 0. I don't know if there may be, no, probably the rest of the y values are decimals. So you're going to have to choose, let's say 4 and 1.3, 7 and 1.9, 4 and 1.4, sorry, 1.4. If I round correctly, they should be 1.4. You can see it right here, 1.38. And 7, 1.9. So now when you do the transformation, what's really going to change when you have a negative x? You're going to be doing a reflection across the y-axis. Okay, so this negative here, reflection across or about the y-axis. That means multiply x values times -1. So 1 times -1, this becomes a -4, this becomes a -7, and the y's stay the same. So -1, 0, 1, 2, 3, 4, -4, 1.4, -7, 1.9, 5, 6, 7. Okay, let's see if we are right. Okay, this was the graph of the original. When we graph the other one, ln of -x. See, there it is. That's the reflection. So ours is more or less like this. Yeah, I messed up that part. As always, I messed up something. So what would be my vertical asymptote here? The same thing, x equals 0. So right here, I'm going to put it over here on the top. Vertical asymptote of x equals 0. Okay, and that's it. Now, the last part on this section. These sections are tedious. There's a lot of little things to learn. The domain of a logarithmic function. Okay, basically, like, yeah, you don't have to read all this. Just know that there are two restrictions for the domain in a logarithmic function. I'm going to put here. Domain of a logarithmic function. Restriction on domain of logarithmic function. The only kind of numbers that you can never have inside of this parenthesis, it's a negative number or the number 0. Okay? Inside of the parenthesis, there should never be a 0 or a negative number. We don't want this kind of numbers. No zeros, no negative numbers. How can we find the domain then? Knowing that those are the only kind of numbers that we cannot have, it means that the inside of the parentheses has to be only positive numbers. It could be fractions, it could be decimals, it could be integers. Doesn't matter, as long as it is not the number 0 and any negative number. I'm not saying that I cannot substitute a negative number or a 0 into this x. I'm saying that after I substitute something, I don't want this to be a 0 or a negative value. So you're going to get, to find the domain, it's very simple, the domain of a logarithmic function. You get the inside of the parenthesis, you set it equal to 0, and you find a way to solve for x. So why don't you simply move this x to the other side by adding it? And that's it, you're done. It's solved for x. The x is by itself on the other side. So x is equals to 5. Now, is this the answer already for the domain? Nope. You have to make a number line where you put negative infinity, positive infinity, place the number that you got, test values, choose a number to the left and to the right. So you choose 6, to the, no, that would be over here, x equals 6. To the left side, you can choose 4. And now you can do mental math. What happens if you plug in these numbers? And here you can do mental math because it's easy. What happens if I put this number here, and also you're going to put this number here? So you're going to substitute those two numbers one at a time into this x. The only kind of number that you don't want to get is a 0 or a negative. So if I put a 4, 5 minus 4, it's 1. That's fine. 1 is a positive number. Perfect. Put a check mark on this side. All the numbers to the left side of 5 are going to work. What about 5 itself? 5 minus 5 is 0. So this number cannot be included in the answer. What about the numbers after 5? 5 minus 6 is a negative 1. We cannot have that kind of numbers. So then you're going to say that the domain is, and you're going to have to write the domain in interval notation form, from negative infinity to 5, excluding the 5. This kind of parenthesis exclude endpoints. Endpoints are the numbers at the end of the parenthesis. This kind of square bracket include the endpoints. So in this case, we do not want to include, we want to exclude the 5, because the 5, when we plug it in into the expression that is inside of the parenthesis, it gives us a 0, and we do not want that. Okay. So that's what the answer would be. You just need to learn when to use the different parentheses according to, are you going to include, are you not going to include that number where the parenthesis is going to end. On the infinities, you always use regular parentheses. Okay. This one. Get the expression on the inside, set it equal to 0, and solve for x. Here, you're going to solve for x through factorization. 5 times 1 is 5, plus, and a minus. 5 times 1 is 5, and subtracted is 4. So yeah, the factorization did work. Minus 5, x equals negative 5, plus 1, x equals 1. Okay. So these are my two numbers that I'm going to use on the number line. Let me do the number line here to the side. Negative infinity to positive infinity, negative 5, positive 1. Choose a number to the left side of negative 5. That can be negative 6. Choose a number in between these two. That can be 0. Choose a number after 1. That can be 2. So what happens now here, doing mental math might not really work. You probably are going to have to set up the substitution and then use the calculator. It's more complicated. In the other one I didn't need to, but in this one I do need. So I want to know what kind of answer I'm going to get with this, with the 0, and with the 2. So with this one, let's see what we get. Negative 6 squared plus 4 times negative 6 minus 5. Wait, I put something wrong. Oh, I didn't put the number here. Because when I click with the writing tool that I have, sometimes it doesn't click correctly. 7. So 7 is that remember, what you don't want, the restrictions on the domain of a logarithmic function, whether it's a logarithmic or a natural log, the restrictions are the same. No negative numbers. So this is okay. No negatives and no 0, right? But this is fine. It's a positive number. Now with the 0 squared, that's going to be negative 5. You can put it on the calculator, but it's going to be that. So we cannot use this. So any number in between these two numbers, nope. Now with the 2, seven. So again, can you use 7? Yes. Okay. Yeah. So the solution or the answer is going to be that the domain goes from negative infinity to negative 5. Now my question is, are we going to include the negative 5 and the 1? Are we going to use square brackets or regular parentheses? Forgot to check for that. So you're also going to have to substitute the negative 5. So here, negative 5. Zero. I cannot include it. What about the 1? I'm pretty sure it's not going to be included. But let me just try and see. I already typed something wrong, I saw. So 0. So no. These two numbers, you cannot use them either. So from 1 to infinity. So with this, you're saying that you can substitute numbers into the x's that are in between negative infinity and negative 5, or in between 1 and infinity, but never using the negative 5 or the actual 1. Okay? And that's how you find the domain of a function like this. Okay? Same thing here, same idea. Get everything you have on the denominator, set it equal to 0. Now, how do you solve for x in a fraction like this? You get the top, you get the bottom, both separately, and you solve for x on both. Plus 1, so you're going to get the x's from the top and from the bottom. And then you do the number line. Uy. Negative infinity, positive infinity, negative 2, and 1. Choose a number before negative 2, negative 3. Choose a number between these two, could be 0, and choose a number after 1, could be 2. So, test them. Negative 3 plus 2 over negative 3 minus 1. And you want to see what that would give you. I don't know why I put a 0. And maybe this would be simple to do. I mean, I put it like in parentheses, but really I didn't need to put the parentheses. We can probably do this without the need of the calculator. Negative 3 plus 2, negative 1. Negative 3 minus 1, negative 4. So 1 over 4. So is this a positive number? Yes. And that's the only kind of number that I can have here inside. Let's do the next substitution. 0 plus 2 divided by 0 minus 1. So 2 divided by negative 1, negative 2. Can I have a negative number? No. So then these numbers do not work. And I'm also going to substitute a 1. I'm sorry, a 2. I was substituting this one. 2 plus 2 over 2 minus 1. 4 over 1, 4. That's okay. But don't forget that we are supposed to check also what happens with the endpoints of my intervals. Okay? So I want to know what happens. So we substituted this one. I also want to know what happened with the negative 2 and with the 1. So let me do it here. Negative 2 plus 2 divided by negative 2 minus 1. What's it like that? Plus 2 minus 1 plus, yeah. So 0 divided by negative 3. 0 divided by any number is 0. Remember, we cannot have the number 0. So this, more than likely, is not going to work. And the last one is trying the 1. 1 plus 2 over 1 minus 1. 3 over 0. It's undefined. This is a non-defined operation. Division by 0 does not exist. So that means that obviously you're not going to say that you're going to include this one, right? This number, the 1. It's an undefined operation. That doesn't even go in the domain. So your solution for the domain is from negative infinity up to negative 2 union from 1 to infinity. Okay, excluding the negative 2 and the 1 using that kind of parenthesis. And this concludes this section. 4.2 logarithmic functions. Okay. Sorry about sometimes pausing, and sorry if you heard noises at the beginning, at least in the first lesson. My dogs were here and they were just making noise. And sorry about the barking. Okay. And that's it. See you.